Liquid thorium reactors cannot suffer a meltdown because their fuel is already a molten salt fluid that expands when overheated. Mid-20th century nuclear research prioritized uranium because its byproduct plutonium was directly usable in manufacturing strategic military warheads. Thorium-232 cannot sustain a chain reaction alone and requires an initial external source of neutrons to begin fission. When a thorium atom absorbs a neutron, it transmutes into uranium-233, which then fissions to release thermal energy. Standard reactors rely on solid fuel pellets enclosed in metal tubes that trap radioactive gases and degrade under extreme heat over time. Dissolving nuclear fuel into molten fluoride salt allows operators to continuously strip away volatile fission products without shutting down operations. If electrical power fails completely, a cooled salt plug melts, allowing the liquid fuel to flow down into underground storage tanks.
Molten salt systems operate at normal atmospheric pressure, eliminating the risk of massive explosive containment breaches seen in pressurized water reactors. The Oak Ridge National Laboratory operated a small prototype molten salt reactor successfully for 4 years during the late 1960s. Nuclear pioneer Alvin Weinberg advocated for safer thorium designs, but was dismissed from his government position by political leaders in 1973. The United States government shifted all funding to liquid metal fast breeder reactors, utilizing plutonium to build strategic weapon materials during the Cold War. Billions of dollars in early state subsidies created a massive commercial infrastructure and supply chain optimized solely for light water uranium technology. Thorium is roughly 3 to 4 times more abundant in the continental crust of the Earth than naturally occurring uranium resources.
Natural thorium consists entirely of the useful isotope thorium-232, requiring no expensive isotopic enrichment facilities before usage. Conventional uranium requires complex gas centrifuge systems to boost the concentration of uranium-235 from less than 1%. High-temperature fluoride salts are chemically aggressive, eating through standard steel alloys and requiring advanced nickel-based metals like hastelloy N. Intense continuous neutron bombardment weakens structural metals inside the core, creating macroscopic embrittlement over decades of continuous operation. Thorium transmutation creates an intermediate element called proto-actinium-233, which requires isolated time to decay cleanly into useful uranium fuel. The thorium fuel cycle inevitably generates small amounts of uranium-232, which emits highly penetrating lethal gamma rays during its decay.
Managing radioactive liquid loops requires custom automated robotic maintenance systems because the intense internal gamma radiation field prevents human engineers from safely entering the containment vault for repairs or routine technical inspections. National nuclear regulatory agencies built their safety approval frameworks exclusively around solid uranium fuel rods, meaning that certifying an entirely separate liquid chemistry system requires decades of bureaucratic renegotiation and billions of dollars in compliance testing. Private venture capital avoids thorium development because building a first-of-its-kind commercial prototype requires massive upfront capital investments over 15 years before achieving regulatory clearance or demonstrating competitive market validation. Thorium waste contains far fewer long-lived transuranic elements like plutonium or americium, which means the total radioactivity of the spent fuel drops back to safe natural background levels within a few hundred years instead of millennia.
Molten salt reactors can utilize up to 99% of the injected thorium fuel resource through continuous internal transmutation, compared to the mere 1% utilization rate achieved by conventional solid uranium light water reactors. While thorium suppresses plutonium generation, the inevitable presence of uranium-232 contamination emits highly penetrating gamma radiation that makes weapons fabrication hazardous and easily detectable, though it does not completely prevent theft by determined states. Strategic defense decisions made during the Cold War locked global energy markets into solid uranium configurations, establishing an institutional path dependency that continues to starve alternative nuclear reactor research of necessary public funding today.
Operating a liquid thorium reactor efficiently requires constructing a miniature chemical processing facility directly adjacent to the main loop to continuously extract volatile fission poisons like xenon and lanthanides without halting power generation.
Internal graphite blocks used to slow down fast neutrons expand and contract significantly under intense localized radiation damage, forcing facility operators to perform highly complex, complete physical core rebuilds every few years of operation. India holds massive natural deposits of thorium and has spent decades developing a specific three-stage nuclear power roadmap designed to transition from heavy-water uranium reactors toward complete domestic energy independence utilizing thorium breeders. China recently activated a 2-megawatt experimental molten salt thorium reactor in the Gobi Desert, testing automated molten salt loops, high-temperature thermal operations, and specialized nickel alloy structural endurance under realistic commercial run conditions. Modern engineering startups are focusing on small modular thorium designs to reduce upfront capital requirements, allowing factory assembly line production methods that bypass the astronomical construction costs and delays of traditional gigawatt-scale installations.
Sustaining core operations above 700 degrees Celsius allows thorium molten salt systems to supply direct, emission-free high-temperature thermal energy for heavy industrial manufacturing processes, steel production, and efficient large-scale hydrogen synthesis. Lithium isotopes present within the primary coolant salt mixture generate radioactive tritium gas under neutron bombardment, which can readily diffuse through hot metallic piping walls, requiring advanced secondary collection and containment systems to prevent environmental leakage. No commercial supply chain currently exists anywhere to extract, purify, and manufacture nuclear-grade thorium or specialized isotope lithium fluoride salts at the industrial scale necessary to support widespread deployment across global energy grids. Closing down a retired liquid salt facility presents unique engineering challenges because the entire internal piping network remains highly contaminated with intensely radioactive salts that solidify into hazardous compounds when the system temperatures drop below operation levels.
The plummeting cost of solar photovoltaics, wind turbines, and grid-scale lithium battery storage makes major utility corporations highly reluctant to invest billions in unproven long-term nuclear alternatives with highly uncertain regulatory paths. Molten salt thorium reactors can be uniquely configured to consume existing stockpiles of hazardous plutonium waste generated by legacy Cold War nuclear programs, transforming a dangerous weapons proliferation risk into clean, usable civilian electricity. Conventional solid fuel reactors suffer from xenon-135 poisoning, which prevents them from restarting immediately after a temporary shutdown, whereas liquid salt systems allow continuous gas bubbling to strip the isotope away automatically. Elevated operating temperatures directly translate to superior thermodynamic efficiency using gas turbine cycles, meaning that thorium molten salt systems convert a significantly larger percentage of atomic fission heat into grid electricity compared to water-cooled reactors. Thorium presents a mathematically proven physical pathway toward clean, incredibly dense baseline energy generation, but overcoming 70 years of global institutional lock-in to the traditional uranium life cycle remains an enormous geopolitical and financial barrier.